So without further ado, I'll pass over to Malcolm for his presentation.
Okay, well, hello everyone. I hope you can hear me okay. Firstly, it's a great pleasure to be here. So thank you very much to Primary Engineer for the invitation. The title of my presentation is this one. I can make my screen work. Half rho v squared s times the coefficient of lift plus passion. And my job as an experimental test pilot. Now, if you don't like equations, don't worry. We'll concentrate a lot on the passion today. But we'll come back to that equation during my speech in just a few minutes' time. So I thought what I'd talk about is how I got to where I am today in terms of being an experimental test pilot, what we do in the job, and give you an example of some of the particular work we do. And then I really look forward to answering any questions you may have. So let's get on. So where did it start? Well, I think it started on a beach in Cornwall in about 1966 when I was 2 years old. According to my parents, I remember nothing of this. An airplane flew very low over the beach, made a very loud noise, and absolutely terrified me. But I cannot remember a time when I did not want to be a pilot. And I do wonder if this incident had something to do with that. So as I got older, I took an increasing interest in machinery. And eventually, probably when I was about 8 or 10 years old, I was lucky enough to have my first ever flight was a helicopter actually. And that really started to confirm what was an increasing obsession and passion for me. I spent an awful lot of time in my room building airfix kits at a time when really I should have been working harder at school. And it's funny, you know, you concentrate on the subjects that you think are going to be valuable in your chosen career. So I really wanted to be a pilot, and I didn't see much use in studying French. So I failed my French exams over and over again. And now, of course, I live and work in France, and I wish I'd worked harder at all my subjects, but there we go. Against all the odds, in my early 20s, I became a pilot in the Royal Air Force. And there's me, probably at the age of 23 or something, with my first proper aeroplane behind me, the Nimrod. And during this time, I learned a little bit more about test flying. Some of my friends had gone off to do this, and it started to appeal to me as a potential way of expanding even more my obsession with aircraft. There was one major obstacle to this ambition, though. I'm not the world's best mathematician. I had to make my way through quite a lot of additional study to get up to the point where I could take on the engineering part, shall we say, that comes with flying. Pilot I had, test I needed to get. And this is where we start to see the arrival of equations. And half rho v squared s times the coefficient of lift is, as you probably know, the equation for lift. And this is what airplanes fly on. This is what makes airplanes fly. But if you notice, as I go on through my career, now as a test pilot, the smiles are getting bigger. And eventually today, the smile is still very much there. And after 30 years of flying, 10,000 flying hours, I still love it. The passion is still there. And guys and girls, if you can possibly find a career that is also your passion, you've got it made. So follow your instincts. So this has been all about me. Let's have a look at my office. So this is now where I work, and I cannot imagine a better office. This is the Airbus A350. Our newest and most advanced passenger airliner. It's a joy to fly this aeroplane. This is an aircraft that weighs over 300 tons at takeoff. And it's majestic. It's fantastic. This is what it's like from the inside. This is what the airline pilots will see. The world's most advanced passenger aircraft cockpit, which we play a role in designing and testing. But before it gets to the hands of an airline pilot, it has to be tested. And this is much more my daily office. And here we see the preparations for the first flight of the A350-1000 series. The test pilots here, dressed in helmets, parachutes, because very early in the life of an aircraft, there are uncertainties. Even in this day and age with computer modeling and simulations, we still don't know exactly what will work and what will not. If we did, we would not need to do test flying. So even in this day and age, we manage the risks and we make sure that we have all the right precautions in place for our flights. Test pilots, but actually test pilots are just a visible face of an enormous team. And if you have an interest in engineering and machines and you want to get into this sort of work, then you will need to be a team player. You will need to work and enjoy working in a group of highly professional people, each with their own skills to bring to the party. And in the back of the airplane, we have flight test engineers. So if you want to get involved in flight testing, you don't even have to be a pilot to fly on the aircraft. We have flight test engineers who lead the testing, monitor the aircraft safety, and manage the enormous amounts of data that we bring in. And this is the flight test engineer station in the rear of one of our test aircraft. And you can see the inside of the airplane is nothing like you will see as you ride as a passenger. A lot of the equipment is not installed because we want to see what's going on in great detail with the structure of the airplane. But it doesn't end there. And here we see a shot of a telemetry station that we have. Everything we do in the air is monitored from the ground for our development flight tests. It allows us to have the relevant experts, the design guys, the engineers who designed and built the airplanes with us in flight. They hear everything we say. They even see us by video as we fly. So we have to be very careful what we do. But the good thing is they can contribute immediately to our flights. They can give us advice. They can give us technical information second by second as we fly. I'm going to show you a couple of videos later in this presentation, and you'll see them in action. So the team is getting bigger, as you can see, but it's even bigger than that. We have the guys who prepare our aircraft, and these two ground engineers are moving a water ballast within our aircraft. If you can see me on the screen here, the center of gravity in a large aircraft is extremely important as part of our testing. If the center of gravity is towards the rear of the airplane will be more lively in handling. If the center of gravity is forward, it will feel heavier to the pilot. It's very important that we test across the full range of center of gravities that we're going to use in service by moving weight to the back of the airplane or weight to the front of the airplane. And the gray pot that you can see here is full of water and is being moved around to give us the center of gravity that we need. We have cameras. We have flight test installation cameras that look at the outside and the inside of the airplane. I hope you can see this shot. It might be behind my video, but maybe you can see a pole sticking out from the side of the airplane that's covered in ice. We have to test the aircraft's resistance to ice buildup. And this is another piece of equipment that we've got to enable us to visualize how much ice is building up on the airplane in bad weather. Here's an interesting test. We have to examine what will happen if the aircraft the pilot attempts to take off at too slow a speed. And the risk here is that we will actually touch the rear of the airplane on the runway. So we have to test this. But look, guys from our team will be installing a bumper under the tail of the aircraft. You can see them on the right there to protect and measure the contact with the ground. These are all part of a huge expert team without which we could not do what we do. So what do we do? Well, there are two forms of testing. Firstly, production testing. Every aircraft that we manufacture for our customers needs to be tested before it's put into service. So we as flight test crews make the first flight of every single aircraft that is built by Airbus before it goes on to the customer. We will then even fly with the customer pilots so that they can assure themselves with us that the airplane is a really good quality and ready for them to put into service. And when you think that in a normal year, okay, let's ignore last year with the COVID crisis, but in a normal year, we push 800 aircraft out of our production facilities. 800 times this procedure has to be gone through 800 flights, absolute minimum. And development testing, which is probably what you imagine test pilots do. This is new aircraft or new equipment. And we have to go through the testing of them to make sure that they firstly function as we hope they will, or that we can improve them if they don't. But most importantly, we also have to convince government authorities that our aircraft are safe to fly, safe to carry passengers. And this is called certification. And it's a lot of what we do is proving that our aircraft work well. So we have handling qualities testing. We also do a lot of work in simulators. Not all of my job is in the air, okay? I spend a lot of hours working in simulators like the one you see on the bottom left to develop cockpits, to develop procedures, and to test how the airplane will work in flight before it even flies. Look at that on the top right. The most important thing of our aircraft for our customers is the cabin. Okay, and we have to test this as well. So here you see a test aircraft cabin. Each of the seats has microphones, vibration measurements, temperature sensors, so we can monitor and design our cabins to give really good quality flying experiences for our passengers. We have to test our aircraft in extreme climatic conditions as well. They're going to fly in Siberia and they're going to fly in Dubai. So we have to take them to hot, cold, high places. And there's our brave team down at minus 54 degrees C. It's not all fun, you know. We have to test our aircraft in bad weather as well. Automatic landing. All of our aircraft can do automatic landings in poor visibility. We have to show that this will work properly. And finally, we also do development testing of new research projects. And here you see one of our aircraft with a highly modified wing. The orange part of the wing is intended to investigate, to research new capabilities to make our aircraft even more efficient, greener, cleaner, and better performing. Performance, takeoff performance. We need to show that our aircraft, to measure what our aircraft will do in terms of using runway and climb performance. Landing performance, including, as you see here, on frosty, icy, slippery runways, which can greatly increase the landing distance of our aircraft. We need to measure that so that we can predict for pilots in the airlines what the performance of the aircraft will be. And let's have a look at an example test. I thought this would be interesting for you. One of the things we have to show during certification is that our aircraft will survive if we penetrate through deep water on a runway at high speed unexpectedly, that the engines will keep running, that the brakes and steering will not be damaged. So how do we do this? Well, we could just fly around waiting for a particularly heavy rainstorm, but that's not very efficient because actually runways are designed to shed water. They're like roads. They slope, they have deliberate camber so that the water will drain away. So it's not very efficient to try and wait for this to happen naturally. So what do? We build a paddling pool. And if you look at this picture, you can see maybe the black squares on the runway just in front of the airplane. These are rubber walls. And we have to fill these little paddling pools with 2.3 centimeters of water. If you imagine that's about ankle depth water. It doesn't sound a lot, but in this picture, the airplane is possibly going 140 miles an hour and weighing about 200 tons. So you can imagine that the force when you enter ankle depth water is very, very strong. So we build this paddling pool across the runway to ensure that we get water pooled to the right depth across the whole camber of the runway. And we divide it to make sure that the nose wheel, the forward wheel of the airplane, goes through one of the paddling pool sections, that the main landing gear, the wheels at the back, go through another section, and that the engines pass over the water as well, because these are the critical parts. So the aim here is to have the airplane entering the paddling pool at exactly the right speed and exactly aligned with the lines you see here, which is quite a job for us as pilots to make sure that we achieve it properly. Imagine also we need to get a lot of data. Each of these runs is very expensive and we could damage the airplane, so we need to get it right. The data we need is video, is photography, but also digital data. And if you see here, I've circled in blue, I hope you can see photographers out on the field. They have to be ready exactly for what's going to happen. We have to inspect the aeroplane after each run to see if it's been damaged. So we have our ground engineers up at the top right, ready to inspect the aircraft. Now, the yellow lines here show the length of the pool. So the aircraft needs to enter the pool, perhaps simulating a takeoff with the engines at takeoff power at exactly the right speed. Now, the problem, of course, as you can guess, the airplane will be accelerating very strongly. So how on earth do we get the speed exactly right when we pass over the first of those yellow lines? Well, the answer is this. We calculate backwards, knowing the thrust, knowing the weight of the airplane very precisely. We calculate a distance that it will take the airplane to accelerate to exactly the speed we want. And then we designate a start position for each run at each particular speed that we need. And then we position the airplane very carefully at that start point using differential GPS. Differential GPS adds a whole level of accuracy to the normal satellite navigation GPS accuracy that you might get with your phone or your iPad or in your car when you're old enough. And it allows us to position the aeroplane plus or minus a few centimeters of where it needs to be. So what I'd like to do, well, I'll just mention also that we leave 3 kilometers of runway ahead of us, because when we come out of that water, going at perhaps 140 miles an hour, we have 3 kilometers of runway ahead of us to check that the brakes are working properly, the steering is still working, and to do something about it if it's not. So I've got a short film which will just show all of this in action. It's quite nice. I hope you enjoy it. There is music and sound, so make sure you've got your music adjusted. And here we go. Let's have a look at the water trough test. See what I mean about a big team? Okay, let's have a look at our latest aircraft. It looks like a whale, but it flies like a bird. The Beluga XL. What is this airplane? It carries no passengers. We build our aircraft using parts from all over Europe and the world. And around Europe, we transport large sections of aircraft to our final assembly lines to be screwed together and turned into finished aircraft. And the Beluga XL is designed by us to do that, to move large parts of our aircraft around. And here you see 2 wings, the wings of an A350, the aircraft you've just seen in that video, being loaded into one of our Beluga XLs to transport to the final assembly line. And look at the inside of this aircraft. It is an engineering masterpiece. It's enormous. It's just flown for the first time. It's just entering service. It's a perfect example of the passion that you can put into engineering. It's not just ones and noughts and zeros and formulas and Greek. It's passion as well. And this video is a video that shows you the highlights of the first flight of this aircraft. Now, there's some things I'd like you to look for during this video. Firstly, again, look at the number of people involved. Secondly, you'll see a view of the telemetry room that I mentioned earlier. Thirdly, you'll see some shots taken in the air, and you'll see in some of the shots a little aircraft flying next to the Beluga. And this is a chase aircraft, which we sometimes use, particularly for first flights. It's able to inspect the outside of the aircraft, give advice over the radio if anything goes wrong. But above all, there are no actors in this video. You'll see crowds of people. They are real Airbus employees. They are the people who have designed this aircraft, who have put it together, who have started to test it. These are the people who've put hours and hours of their working lives into this aircraft, and the emotion that you see is genuine. This is the passion I'm talking about. So let's enjoy this video. Science and passion, if you can put them together into engineering, you'll have a wonderful career, and I thoroughly recommend it. I've spoken too long. I could talk about this all day. I'm quite happy to stay to make the questions slightly longer, but here we go. I'm quite happy to take any questions you may have. Over to you, Nicole.
Wow, it's hard to fathom how large that aircraft is. It's huge. So what was it like flying that? Can you tell a difference between that plane and, you know, a typical A350 that you've flown?
That's a really, really good question, actually, because the Beluga XL is based on the aircraft that you see on the screen now, the A330. We've just added a whole huge new part to the fuselage. And actually, our aircraft, and indeed most modern airliners now, are what we call fly-by-wire. So the response the pilot gets from making a control input on the stick is controlled by computers. So we can actually make the airplane feel very, very similar. So all of our aircraft handle in a very similar way, despite their size. So actually, inside the Beluga, it's sometimes hard to remember you're not actually flying a 330 like you see on the screen here. It's when you get outside the airplane that you realize what's behind you all that time.
So just before we carry on, I'd like to remind everyone that there's a Q&A facility at the bottom of the screen. So if you want to put any of your questions in, I can pose them to Malcolm. And also because we're going to go over a little bit, maybe by 5-10 minutes, so we can get everyone's questions answered. So we do have quite a few questions in the Q&A. So someone called from Cooper said, how long did it take to design and build the Beluga aircraft?
Right. So typically, for one of our large aircraft, the design process takes between 5 and 7 years. So that's from saying, okay, we're going to do this, through all of the development, planning, the early testing of, we integrate systems in the simulators. I showed you a photograph of those. So we have to put all of the systems of the aircraft together, test them, build them into a final aircraft, and then start to fly. So that process is between 5 and 7 years. We always try to make it as efficient as possible. And then a full flight test program on a new aircraft type will take about 18 months to 2 years, depending on the complexity of the project.
So it's a long process.
It's a long process. These are major pieces of engineering, yeah.
Mm-hmm. And Cooper has also asked, what kind of materials do you make the aircraft from?
Well, the Beluga has significant metal still because of the nature of the airplane, the structure of it. But our newer aircraft, like the A350, we're now making as much as possible from composites. If you look at an unpainted A350, which is the aircraft I showed you in the water trough film, the vast majority of the fuselage, the body of the airplane, is not a metal color, it's carbon fiber. The very front of the airplane around the cockpit we build from metal still because it needs to be protected against impacts with even birds or lightning. But a lot of the structure of the aircraft now we make from composites. It allows us to build them stronger, but it also allows us to build them lighter for the same strength.
Mm-hmm. So I do have a question from my brother. So yeah. I have an older brother who is absolutely obsessed with aviation. He plays games like X-Plane and Microsoft Flight Simulator. So he personally wanted to ask you, are those kind of good ways to get involved in aviation or flying and getting inspired to become like you?
We didn't have such games when I was starting out, which is probably a very good thing because I would have done even less work at school and probably but we did have my FX kits. How does it help? Well, I do think actually there is something to be gained in terms of what we might call the hand-to-eye coordination that's involved in flying an aircraft manually. So it's not bad training from that point of view, but what you can't get in a flight simulator, of course, is the physical sensations of flying, the G-loads, the turbulence, the feel of the airplane as it moves through the air, which is very important, particularly in some of the maneuvers we do in flight tests. It's a good start. It will certainly be a positive thing. But if you want to fly airplanes, you have to go and do it. And I would encourage anyone who even thinks they would like to get involved as a pilot, just to firstly hang around airplanes, go to a flying club, go to an airport, see what's going on. If you can manage it, get a trial lesson. at a flying club or a flight school, and just see what it's like, see how it feels. If it energizes you, if you enjoy the real sensation of flying, you'll never lose it. You'll never lose it. So yeah, these things are a good start.
Yeah. So Zoe has also asked, how many flights? So you've done 10,000 hours. How many flights do you think that is?
Oh my word! I really couldn't tell you. I suppose if we average it out, it's probably about 3,000 flights. I sort of thought, these are my old logbooks, okay? Each page of this is sort of a couple of months of flying. So 10,000 hours is, what is it? It's about 1 year and 4 months or something off the ground. So I've spent 1 year and 4 months of my life not on the surface of the earth, which is quite nice, really, and I still love it.
Poetic. So Katie has said she's flown a plane herself, and she was just wondering what technology or machinery would make your life easier as a pilot and a tester.
Really good question. And this is what we're always trying to do, actually, Katie. We're always trying to make life easier for the pilot, because the more we can reduce the pilot's workload in actually flying the aeroplane, the more mental capacity the pilot has to handle problems, to navigate, to see, to keep situational awareness around them. So I think the fly-by-wire, the flight control system that we have in our aircraft is intended to make them much easier to fly. Katie, you've probably dealt with trimming the aeroplane. You don't have to trim an Airbus, it does it for you. The navigation systems are intended to be very easy to use and make it very clear where the aeroplane is at each stage, and what phase of flight the aircraft is in. So there's two main ways we can do this. As I say, we can make the airplane easier to fly when the pilot is manually flying the airplane, and we can make the systems easier to use. And we're always striving to do that. And if anyone has good ideas, then tell me.
So Chris is also, he said, fantastic presentation as well, Malcolm. So his question is, what are some of the problems Airbus or aviation and aerospace engineering face that pupils could think of to design a solution to during the competition?
Wow.
I suppose that's similar to the last
such good questions today. Engineering solution that you could help us with. Where to begin? You could think about this. Our aircraft are big, heavy aircraft with complex systems, but a cockpit that we try to make the same as much as possible between all of our aircraft. So if you climb into a Beluga XL, the cockpit is almost identical to the A330 that you see on your screen here. And it would be very similar to the A350. If you climbed out of an A330 and you climbed into an A350 for the first time, you would recognize everything. It would look familiar. You would be able to fly it. So I wonder if people would like to think about how we would train new pilots for that. How we would introduce those into a basic training airplane, something you would fly from a little airport near you on your first flight, maybe like the aircraft Katie flew. I don't know, Katie. How might we introduce those systems to a pilot very early?
That's something for them to think about then, isn't it?
Yeah.
Katie's also asked, were you an RAF cadet before you went into the forces?
You know, I wish I had been, but I was not. But it would have been a very good idea. So if anybody doesn't know about the Air Training Corps, have a look online at what they do. I'm guessing maybe Katie is, in which case she'll probably recommend it. But there are opportunities, if you join the Air Training Corps, there are opportunities to fly, there are opportunities to do gliding, and there are opportunities to make visits to airports, to hear presentations, to do little bits of training. And I think it's a great introduction, and I wish I'd done it actually, but no, I didn't, Katie.
Do you think that would be good experience before they entered into that kind of training to be in aviation or to be like a pilot? Do you think that would give them like a good foundation for them to start building on?
It really would. If you want to be a pilot, then you would get the opportunity to fly in a light aircraft, and you would be able to decide quickly whether you like it or not. You know, if it's not for everybody, and there are plenty of openings in aviation, in engineering, aircraft that don't involve flying. Okay, so if flying is not actually your thing, but you love airplanes, you can still work in this field. And the Air Training Corps gives you exposure to the other sides of aviation as well. You don't have to want to be a pilot to join the Air Training Corps. You could equally make it a springboard for a career in engineering, for example, ground engineering on the ground.
So what kind of skills do you think you need outside of the classroom that would be beneficial for being an experimental test pilot?
I think you need a strong sense of self-preservation. And I say that with a smile on my face, but it's really true. I think there's, I mentioned at the beginning of my presentation, there are risks in flight tests, but they're very closely controlled. And we take a keen interest in assessing the safety of everything we do before we do it. It's a very methodical approach, and you'll see it across engineering, not just in aviation. But we're very methodical in the way we assess safety and make contingency plans and prepare for our flights. So I think you need that methodical approach to effectively looking after yourself and taking care of the team. You do need to be able to concentrate, to be able to focus attention in the right place when other things are going on, know what's important and prioritize. And I know I've said it a few times, but you really need to enjoy what you're doing. And if you can follow your passion, make it your career, whatever you go into, then that's the way forward, because it makes life so much easier.
You never work a day in your life.
Sorry.
You never work a day in your life if you do something that you enjoy.
Exactly. Well, there are a few meetings to attend as well.
So we have had an anonymous question. So
yeah.
Will we have planes fueled by alternative energy like solar powered, or will that be a norm in the near future?
Then about the near future, it depends what you mean. But we certainly in Airbus, we recognize that the future is going to be in alternative means of propulsion. So one thing in aviation, and in particularly in flight test, is you try to make steps incrementally, because that's a safer approach in terms of actual safety, but it's also a less risky approach in terms of in industry and engineering. So at the moment, our aircraft now, we're already building them so that they can take a mix of biofuel and conventional fuels. And I think for the next few years, that will be where the industry will concentrate on making the fuels that our existing aircraft are using more efficient and greener. We're also always working to make the airplanes consume less fuel. So that's the ongoing work. But the real question is the next step. And yes, we just announced, in fact, last year that our big future project will be a completely new form of propulsion. And the way we're working at the moment is towards a hydrogen-based power plant.
Mm-hmm. And I think the same person has also asked, will there always be a need for human pilots, or do you think that AI will start to take over that piloting?
Another good question. Aircraft have become increasingly automated over the years, as we probably all know. That has been intended as I mentioned in my answer before, to make life easier for the human pilots, of course. Our point of view is the aircraft are there to move the public safely from A to B, to provide safe and efficient transportation of people. And we will follow whatever is the most appropriate technology. At the moment, our strategy is to use automation to assist the human pilot. And there is no plan by us to remove the human pilot from the cockpit. If that turns out in decades ahead of now, if that turns out to be the best and safest way of operating due to the development of technology, then maybe we will do that. But that's not our strategy. Our strategy at the moment is to support the human pilot, make life easier and safer.
Mm-hmm. So Katie, she's on fire. There is a new technology for space exploration where instead of using fuel, they take in the vacuum of space and pump it pumping it full of protons, which is used as thrust. Could this be possible with aircraft?
Gosh, I'd have to open my engineering mathematics book again. I don't know if we got really high into the atmosphere where we're approaching space, hypersonic regime. I suppose we could look at that. Our emphasis for mass transportation at the moment is much more in the lower atmosphere, moving large numbers of people. But there is a market, I'm sure, for low volume, high speed transport. But it's not an area really that for us in Airbus we see ourselves going at the moment.
There is a push for commercial in companies like SpaceX who are trying to make commercial space flights. Do you think that is something that you wish that you could have tested? Because it's going to be another couple of decades, I think, before that kind of starts kicking off. So is that something that you would have liked to have explored?
Well, I have friends. It's a small world in flight test. I have friends who are doing that testing for people like Virgin Galactic at the moment. But in some ways, yes. In some ways, yes. But they fly not very often, and it's very, very short. They're flying, so it's very exciting, very, very short. Whereas I fly 4 or 5 days a week, and I love to be in the air. Would I like to do it? Yes, I would love to. I would love to do any new experience related to aerospace. Of course I would, yes. But I'm very content in my present job, and I wish them all the best.
It's kind of a leap into the unknown, really, isn't it?
Never. No, we always try to know as much as possible before we leap.
So we're kind of running out of time. One last question from the Q&A. Why can't planes reverse?
Why can't they reverse on the ground?
I think that's the question. Yeah,
they can. Some airplanes can. I flew an airplane in my military career where quite frequently we would reverse. It's possible with propeller aircraft. It is possible with some jet aircraft. A technique called power back, but it's not recommended for most jet engines, and we don't recommend it for our aircraft. In fact, it's not something we allow on our aircraft, largely because it's quite difficult to control the speed at which you're reversing. And with a jet aircraft, there is a tendency for the hot jet exhaust to be recirculated into the front of the engine, which can increase the temperatures in the engine. So it's not a great idea in a jet aircraft unless the aircraft's specifically designed for that. But in a propeller aircraft, a lot of aircraft, they can very easily reverse. Yeah.
Okay, well, for my last question, do you have any final parting words or advice for the young engineers that are watching today?
Yes, if you had asked the 22 or 3-year-old me, the young kid in a flying suit in front of the Nimrod 30 years ago, whether he would ever see himself as an experimental test pilot at Airbus, I would have laughed in your face. I I would have thought it impossible. But here I am. So it just goes to show if you really want to do something, okay, there's a little bit of luck involved, but also have a go for it, dream high.
Okay, well, thank you for that. Thank you for taking time out of your short hours on land to be with us.
No, it's a great pleasure.
So hopefully people have been inspired by this presentation and interview with Malcolm from Airbus. If you want to get inspired any further on the competition, then go to www.leadersaward.com, and there's loads of resources there that you can look through. But yeah, we'll leave it there. Thank you, Malcolm.
Nicola, just one more point I meant to mention. If you want to see more videos like the ones I showed, have a look at our YouTube channel, Airbus.
Yeah,
there's lots of them there.
All of the socials are on the screen as well, so you can go have a look on there.
Absolutely.
Okay. Well, thank you, everyone. Have a good rest of your day.